Refinement of 1D home with sequential pruning. As proved by, the number of states used in a 1D home can have a strong influence on recognition rates. The problem of the optimal selection of the structure for an home is considered in. The first part of this paper presents a method of improving the determination of the optimal number of states for an home. These authors then proceed to prove the equivalence between I, a 1D home whose observation vectors are modeled with multiple Gaussians per state, and 2, a 1D home with one Gaussian per state but employing a larger number of states. According to the authors, there are several possible methods for solving the first problem, for example cross-validation, Bayesian inference criterion, BIC, minimum description length, MDL. These are based on training models with different structures and then choosing the one that optimizes a certain selection criterion. However, these methods involve a considerable computational burden, plus they are sensitive to the local greedy behavior of the home training algorithm, i.e. the successful training of the model is influenced by the initial estimates selected. The approach proposed by addresses both the computational burden of model selection, and the initialization phase. The key idea is the use of a decreasing learning strategy, starting each training session from a nearly good situation derived from the previous training session by pruning the least probable state. More specifically, the authors proposed starting the model training with a large number of states. They next run the estimation algorithm and, on convergence, evaluate the model selection criterion. The least probable state is then pruned, and the resulting configuration of the model with one less state is used as a starting point for the next sequence of iterations. In this way, each training session is started from a nearly good estimate. The key observation supporting this approach is that, when the number of states is extremely large, the dependency of the model behavior on the initial estimates is much weaker. An additional benefit is that using nearly good initializations drastically reduces the number of iterations required by the learning algorithm at each step in this process. Thus the number of model states can be rapidly reduced at low computational cost. In order to assess the performance of their proposed method, these authors tested the pruning approach and the standard approach, consisting in training one home for varying number of states, with BIC criterion and MNDL, mixture minimum description length, criterion. These two strategies are compared in terms of I, accuracy of the model size estimation, 2, total computational cost involved in the training phase, and 3, classification accuracy. In all the homes considered in this paper, the emission probability density for each state is a single Gaussian. For the accuracy of the model size estimation, synthetically generated test sets of 3 known homes were used. The author set the number of states allowed from 2 to 10. The selection accuracy ranged from 54% to 100% for standard BIC and MNDL, and from 98% to 100% for pruning BIC and MNDL, with up to 50% less iteration required for the latter. Classification accuracy was tested on both synthetic and real data. For the synthetic data, the test sets used previously to estimate the accuracy of the model size estimation were used, obtaining 92% to 100% accuracy for standard BIC and MNDL compared to 98% to 100% accuracy for pruning BIC and MNDL, with 35% less iterations for pruning. For classification accuracy on real data, 2 experiments were conducted. The first involves a 2D shape recognition problem, and uses a data set with 4 classes each with 12 different shapes. The results obtained are 92.5% for standard BIC, 94.37% for standard MNDL, and 95.21% for pruning BIC and MNDL. The second experiment was conducted on the ORL database, using the method proposed by. The results are 97.5% for standard BIC and MNDL and 97.63% for pruning BIC and MNDL. The classification accuracies are similar, but the pruning method reduces substantially the number of iterations required.